Hello, everyone, and welcome to the OCX Webinar Week. My name is Irina, and I'm very happy to have you all here. This series is a part of the lead-up to OCX 26, which will take place in Brussels. It's the place where the open collaboration community meets to connect, learn, and exchange ideas. If you haven't registered yet, the link is in the chat. Don't miss it. Today, we are joined by Frédéric Desbiens and Sebastian Schildt, who will be sharing a few demos. Feel free to post your questions throughout the session using the chat or Ask a Question tab. We'll go through all the questions together at the end of the presentations. And make sure to stay until the very end because we'll have a live raffle giveaway for our attendees. All right, let's get started. Sebastian, over to you.
Yes, thank you very much. I hope my screen is shared. So I have...
Just 1 second.
I'm clicking. Yeah, I see things coming up. Now I see at least my slides. Yeah. So I will give you hands-on with Eclipse KUKSA. Hands-on means, yeah, we really get our hands dirty, but since I'm working for ETAS, which is a subsidiary of Bosch, so a large company, we are also very good with PowerPoints. So I will give you a bit of introduction before we get our hands dirty. So Eclipse KUKSA, yeah, obviously it's an Eclipse project, it's an Eclipse SDV project. And what it does is it's an implementation that runs in the vehicle that can provide VSS signals or the VSS signal tree. So applications can interact with VSS signals. And I think for some of you, and I already looked at the audience, that's, yeah, you know what it is, but we might have also newcomers who say, okay, what's this about? What is VSS even? Why do I want it? And why do I have an Eclipse project for that? So I will really quickly give you the rundown of that because we have like, a little bit less than half an hour for everything today because there are other exciting stuff coming up. But you will also, I guess, get the slides later, and there's a lot of information about this also online. But for a quick overview that we can do right now. So there is something called VSS, and you will hear this word quite often in the software-defined vehicle space. And it is called Vehicle Signal Specification. And to explain what it is, you need to think about it as a dictionary for automotive data. So the thing is, there is many data in a vehicle, and most of it not very surprising, right? Like what is the temperature inside the car? Are your doors locked? How fast you are? Which position you are? And in our industry, there are not so many standards or too many standards, maybe how to express this data. And a VSS is a very simple and therefore powerful one where industry agreed upon how to model certain things. And you can see already some examples here, like a charging current, that you at least define what the data type, what is the meaning behind this data point, what physical unit it uses. So it's really, you can think about it like a dictionary, like a vocabulary. And if vehicle applications agree on that, then we are at least one step closer to interoperability, which is still a big challenge in automotive. This dictionary, as I call it, is, I mean, luckily not printed out in large books, but it's machine readable. It's a YAML-based format. It is an open source project. In this case, maintained by the KUKSA organization, which is also partnering with Eclipse on certain things. So it's really like fully open source. You can use it royalty free in open source projects as we do in Eclipse. You can also do it inside your company if you have some projects around VSS. And again, you will see in the demo what it's about and get an intuition. Otherwise, there's loads of material available online. The main thing and the most important thing about VSS is it's a dictionary, but it's not a serialization. So just because VSS defines vehicle speed, it does not tell you which bits and bytes you would need to use to transfer it over the wire. It's also not an API. So it defines the vehicle speed, but it does not tell you like how would the function call look like to get that? Would it even be a function call? That is out of scope for VSS. And therefore, it's also not tied to a specific technology. That's framing it positively. But in the end, VSS is one building block. And if you ask the VSS community where VSS should be used, obviously, the answer is everywhere. And everywhere means if you have a data model for signals, that might be nice in your cloud, right? If you have managed your fleet and you have like 100,000 of vehicles and you want to store the data in an interoperable way, maybe use VSS. If you have these nice companion apps on some OEMs, have them using VSS where you have your phone application and say, please, put the air condition on in my car, or where even is my car, or unlock the car, you could use VSS. On the vehicle computers themselves, like the central computers, the very powerful ones, where normally we talk a lot about these SDV and fast-moving software world, there you could use VSS just to make things more pluggable, more interoperable. And you can go deeper into a vehicle and think about the very low-level ECUs that are controlling certain aspects of your car that may not even be connected to Ethernet, but have buses like CAN and LIN. Maybe there you can use VSS in development or live. That's like the theory on VSS side, and it's easy to say for KUKSA because they just define the dictionary, right? Everything else is homework for organizations like, for example, Eclipse or other projects or companies. And this is where KUKSA comes into play because Eclipse KUKSA realized VSS on vehicle computers. So basically this level, it may be the central vehicle computer, maybe your infotainment, your head unit, however you call it, there you can run Eclipse. And a very quick architecture of Eclipse KUKSA is you have this main component, the data broker, and we will see it in a moment. That is running on such a vehicle computer, and it provides an interface for clients, for example, your head unit or your SDV maintenance application, things like that, telematics applications who can talk to the data broker and request data from this dictionary. They can ask what's the vehicle speed, what's the position of the car, what's the door lock status. And since that VSS part is standardized, it's super nice and they're portable across vehicles. And the example you see here is a dashboard, for example, from Automotive Grade Linux, which is another project that is integrating Eclipse KUKSA. But since cars are complicated, so they are not so standardized as VSS would make you believe. If you look down in the car, how it's realized, and that is very non-standardized. So the actuators, the sensors you have in the car. So therefore, in the KUKSA architecture, you always have something which we call providers. And the providers basically synchronize the state of the vehicle to the state that is expressed by the API. So for example, a data provider would be a provider for vehicle speed, and it makes sure that if your vehicle drives at a certain speed, that this speed is also represented in the VSS model. And then let's say one step more complicated actuation providers, because applications are of course most interesting if they can do something. So they have the task to synchronize the state that you wish for on the API level down to the vehicle. Like if you have a VSS application that says open the trunk, then you need to have an actuation provider that for a specific car knows actually how to do that. At that, magically, you have portable applications. Yeah, short fact sheet. So KUKSA Data Broker, the main component itself, is written 100% in Rust. It's really designed to be lightweight, so not to be run on vehicle computers we have in 3 years' time, but run on vehicle computers we have today. So if you put it in a container, the whole container is less than 10 megabytes. We have run it on platforms that have less than 64 megabytes of RAM, and still there's then some RAM to spare. The interface, like how the applications interact, is based on gRPC. In case you know it or don't know it, that means it can be used virtually in any language and any platform, any programming language. There are many examples around it. We don't have time to look into all of them, but there are these providers that connect to CAN. Some have here GPS as examples. It has an authorization concept. We have some SDKs. We will see some of that. And it has support for a standardized WebSocket protocol. Yeah, but to not waste too much time with the PowerPoints, we will go into the demo and what we do in the demo. By the way, later there is a link where you can also find the cheat sheet and the demo scripts online. So again, we have some example of an E architecture on the right side, and we have this KUKSA architecture on the left side. And what we will do step by step is we will run the data broker, and I'll show you how that is working. Then we will mock some data from global ECUs. So we will try to put data into this API, and then we will write user interface that the driver might see. And our example here is brake pad wear, so like that you know when you need to service your brakes. And with that, let's leave the slides for a moment and go to why you're all here, lots of terminals. So what I do here now is remember, first we need data broker. That's the main component. That would normally run on your vehicle computer. I will just start it because it can also run on your PC. You can see it in this terminal. I started it, it's sitting there. And now for, let's say, debugging purposes, there is something called the KUKSA client. So it means it's a debugging tool. I can basically connect to it. That's normally what an application that you would write for an SDV vehicle would do. So I started the client now here in the black window, and I can do stuff. So let's ask KUKSA about the vehicle speed. So get value vehicle.speed, and surprisingly, you see nothing. That's not entirely true. You see that the path exists. You can also vary the KUKSA data broker for the metadata of vehicle speed, and then you can see part of this VSS model. It tells you I have this data point, it's a float, it's in kilometer per hours, it's the speed of the vehicle. We can also, then what we would in a vehicle, we can set the value of vehicle speed to 200. That's maybe fast, but let's see. And now if I get the value again, I can see value is set 200, and I can see also last time it was set. So that is nice. What we are interested now was the wear of the brake pads. Luckily in VSS, there is already data for that as well. So here you can see the typical VSS part. Vehicle chassis axle, row 1, wheel left, brake, pad wheel. So those things can get long, but that is like a standardized VSS path. It exists, it's a sensor, it says brake pad wear is percent, 0, brake pad is fine, 100%. Yeah, maybe you can already see through it. So that's the definition on the VSS side. And that basically is, so what we did now is we started on data broker, right? And manually with the debug CLI, we looked into it and we get the feeling for that we can get and set certain sensor data. What we will do now is, I mean, I can't in this short time set you up a full CAM-based ECU here, but we will write a small script that will try to feed this brake pad wear data into the data broker. To do that, let's go to the green terminal, and I make a new folder, OCX demo. And so see, I'm not cheating. It's a super empty repository. However, I will of course not do everything from scratch. So let me get the example in. Now I copied basically one file, this data provider. So because what we want to write now is the data provider, something that magically gets the brake pad sensor data and puts it into data broker. And if we look at the code, again, it will be shared later. You can ignore most of it because the interesting code, the other one you will see when I execute it, the interesting one is just the main loop. The main loop does something like it is connecting with the VSS client to the KUKSA server we have running here. That would also happen in your car, right? The application would connect to the local data broker. Maybe in a car you would write it in Rust, but anyway, now we want to be fast with Python. Basically, this application here for demo purposes, it will ask which brake pad we want to update, which value, and then it will just do this update value function, which is part of the KUKSA SDK. Let's see, it works. Before it works, we need to install our KUKSA SDK for Python. That is already installed. All I need to do now is Python data provider. And also before we do that, let's go back here to the black client. Now you see you can also use wildcards in the GET request. So now I get the data of all the brake pads. And you can see basically they all exist for brake pads, but there's no data in it. Now we are starting our data provider. We are starting it using the correct port. And you can see it asked me here which brake pad I choose. Let's say the front left I choose. And let's update the value to 15. Then it says I update brake pad data. So we go back here. And we can see that one of the brake pads, so that is axle row 1, which is front in VSS, the wheel on the left side. So that is what we choose here, front left, has a value of 50. And just for testing, let's do another one, rear right, set it. And now we have the 50 from before, and we have the 2 that we just set. And of course, in a vehicle, that would be a component that runs continuously on your central vehicle computer or even another ECU, and that would provide this kind of data. So that application that require it always fit. So that is if we quickly go to our, if we quickly go back. So basically now what we did is make a very simple simulation of these providers here that would continuously feed the data. What we now do is, because why do we want to use the data? Maybe to show the customer on its phone or on the head unit when he needs to service the brake disc. So let's do that now. Write the driver UI for that. And let's use this window for that. We are going to the same folder. So far, only the data provider is in. Copying again. Right here. And I will show you the code in a moment. But actually, what we do, this one now is a web app that's written in HTML, so you can see index and some JavaScript. Maybe let's quickly look into the JavaScript, because here we are using now not the gRPC-based protocol that the provider is using, but we're using a WebSocket-based protocol, VASS. That is obviously not as performant, but if you really write applications with, let's say, HTML5 JavaScript text stack, that's of course very easy. But you can see quite, it's quite simple. You subscribe certain values, because that is also a feature of the data broker that you do not always need to poll it, but you can subscribe and tell it, please keep me updated what happens to all these padwares in this example. And the rest is some JavaScript magic to handle the WebSocket. But I think also it is best seen live. So what I do now is I'm starting a small web server here. Maybe I have Python 3. So now it's serving our web app. Let's make this smaller. Right. And so that is basically the web application. And now just to double check, it shows 50, I don't know, and 2. And that fits also the last values we did here in the in this example, right? The first row left is 50. For the second row right is 2, and the other 2 we don't have values, so the application can't show it. But now let's say this would run on the dashboard. So if now we change it, let's say the front right hasn't been set yet. We set this, and immediately you can see the value is updated on the page. Or let's see the right left. Maybe we did not do maintenance for a long time, so that one is really broken now. And that's as simple as that. And the nice thing with VSS now is that this application we wrote here, that only uses VSS data. So that would run on any vehicle, and the data broker would run on any vehicle. Only, of course, the providers are the one where you need to adapt. But again, now we made this example. In the KUKSA project, there are also some providers, for example, for CAN, which you can just configure that some data can be easily. And with that, let's go back to our slides. So basically, we have seen data broker running, manually used it. We wrote this mock provider to provide the values. We have written a UI application and could see that live, if some data is changed here, immediately it comes out here. And in now, I don't know, maybe 10 minutes or so, we basically used this tech stack, right? We have the data broker, it's written in Rust. We have the data provider. We use the Python API or the Python SDK that internally used gRPC to talk to data broker, because that is our main data broker API. If you don't want to use Python, there's a Rust SDK, and you can also spin your own in any language you like. So they were quite flexible on this. And then you could write applications also based on gRPC, but we have used the VASS protocol. That is a protocol that was first developed by W3C, and now it's taken over by KUKSA. That's a WebSocket-based API to access VSS data, also supported by Databroker. The advantage was we could just use HTML5 and some JavaScript and create these very simple UI, but again, it's just maybe 150 lines of code. You can check it out later and maybe make it nicer. I guess there's still room for improvement. But my main point was it was really easy. If I can do it now, live here in front of you with all the pressure, then of course at home you can probably do it in half. So to sum up and to put the, let's say, marketing pitch for KUKSA, so that is currently the go-to platform if you want to provide the industry standard VSS data inside a vehicle. There are other solutions, like you may want to use VSS in the cloud. That's a good idea. That's maybe not what KUKSA is specifically for. You may want to use it on a microcontroller, like very small one. There's solutions for that, but maybe not KUKSA. But in a vehicle, on a vehicle computer, then Eclipse KUKSA is the way to go. And that has, I think, also proven a little bit, because it is the standard VSS component in automotive-grade Linux, which is a, let's say, Linux distribution that is tailored for automotive use cases. And they use VSS as their data model for all the UI-facing things, and they have integrated KUKSA in their distribution. And as I said, there are many other things than Python. You can use Rust. There's a Kotlin SDK. We have a mock provider that can do a little bit more. We have a CAN provider that really can live, transfer CAN signals. And also, there are more complicated examples than this breakpadware example. So on the blueprints, on the Eclipse SDP side, there's the signal to service blueprint that shows, I think, how you can use a horn. Some other components, a fleet management blueprint that shows like how would you use KUKSA to gather data from a vehicle and then putting them in a backend, for example, your fleet of trucks. In the KUKSA project itself, there's the Android companion. That's the simple Android application that can switch on the lights, open and close the doors, and show the state on the KUKSA side. Again, there's the GitHub where you can find everything. And that brings me to the end of the first part. So thank you very much for listening until here. I understand for questions we have time later, but for now, we have the next exciting topic coming up. If Frédéric is still online, he is very good.
Probably. So let me restart the camera and everything and share my screen. And we'll be on our way. By the way, Sebastian, it was interesting, your presentation. And it shows a bit how old I am, because you kept repeating about VSS, and all the thing that came to my own mind was visual source safe. I don't know if you ever stumbled on that one, but really it was a nightmare. And you will have to stop sharing your screen, Sebastian. It seems the UI is telling me that only a single screen can be shared. So thank you very much. And I will share mine now. One moment. All right. So thank you, everyone, for being here. So if you don't know me, my name is Frédéric Desbiens. I manage embedded and IoT programs at the Eclipse Foundation, and I'm also the project lead for Eclipse ThreadX. And so before we get into the actual demo, just a few minutes of information about what ThreadX is and what it can do for you. So Eclipse ThreadX has been around for a while. So initially it was first, Eclipse ThreadX is a real-time operating system written in C, targeting microcontrollers and other embedded system on a chip. And so when Sebastian was telling us, KUKSA, the data broker is fairly lightweight. It's about 10 megabytes. We can run it on boards with 64 megabytes and things like that. That's great. In the case of ThreadX, it's a bit smaller since, we can run on 64 kilobytes or less. And as you will see, that's exactly what I will do during my demo. Anyway, so ThreadX initially was a commercial product, started in 1997 by a company called Express Logic. And then in 2019, Microsoft acquired Express Logic and renamed the whole stack Azure RTOS. So maybe you're familiar with that name. Let's say that after a few years, they realized that this was not necessarily a commercial success, but rather than killing it in 2023, Microsoft decided to contribute Azure RTOS to the Eclipse Foundation and to contribute the ThreadX trademark at the same time. So ThreadX and Azure RTOS then became Eclipse ThreadX, which is now available on GitHub under the very permissive MIT license. Now, when we say ThreadX, ThreadX is the name of the real-time kernel inside the system, but there are other components. So there's a file system, FileX, a USB stack, USBX, a network stack, NetX Duo, and then a set of GUI widgets that you can use to build user interfaces, which is called GUIX. And finally, TraceX, which is a traceability tool that you can deploy on your Windows laptop in order to instrument in real time the behavior of your application. By the way, ThreadX is also available in an SMP version called ThreadX SMP. We are really original with our names there. But in any case, if you have a multi-core system on a chip, then ThreadX SMP, if it supports your SoC, will be able to schedule threads across all the cores available on the SoC. ThreadX has the distinction to be the only real-time operating system in the market which is both open source and certified for safety critical applications. So you see all of the standards mentioned on this particular slide. I won't emphasize this today. The focus is on the code, but really, if you are looking for an RTOS which is both open source and ready to go in cars, medical devices, electronic devices, or even trains, then ThreadX is the only open source option right now available in the market. Now, looking a bit closer at our various components. So ThreadX, our kernel, can be small. And then when I say small, really small, so the minimal footprint for it is 2 kilobytes, okay? And this means you would deactivate most of the features. So maybe it's not that useful at that size, but it can get really small. And you will see that's actually the case in real-world applications. One of the great things it does is that it's really been optimized for size and speed. So you can get sub-microsecond context switches from one thread to another and things like that. And if you use an optional feature that we've got, you can even enable modules with memory protection, which means essentially that threads will be able to address isolated memory areas and won't be able to write outside or to read outside of those particular areas as needed. So if you're trying to build something a bit more robust, then the memory protection modules in ThreadX are certainly a very useful feature to leverage. Then we've got NetX Duo, which is something I will show you today in the demo. So it's small, really. It can fit in 50 kilobytes and really brings near wire speed in terms of, It brings near wire speed in terms of performance, and at the same time, it will result in minimal CPU usage. So even if you have a very constrained type of microcontroller, it's a good fit nevertheless. And in this case, it will leverage extensively zero copy and auto scaling behind the scenes to make sure that we use the resources available as efficiently as possible. Now, the parts in gray in my diagram are really the parts that are safety certified. So the IPv4 and IPv6 support, the TCP support, TLS, and then the MQTT client, which is something I will demonstrate today. Then we've got FileX. FileX is a very efficient implementation of the FAT file system, and it supports FAT12, 16, and 32, so you can get multi-gigabyte volumes without any trouble there. And one interesting thing about it is that it integrates something called LevelX. So if you use NOR, NAND, or flash storage, SD card, those kind of things, then essentially with LevelX enabled, and this is transparent to the developer, you'll be able to level the wear on your flash storage or SD card, which means that you will make it live longer. Then USBX. USBX is not something I'm showing today, but essentially USBX is a comprehensive USB stack that supports several proprietary host controllers or device controllers. And so you can use it in host mode, which would be something you plug a keyboard on, for example, or you can use it in device mode, which means this is literally ThreadX running inside a keyboard, for example, to drive the keyboard or something else of that nature. And it's really a very nice USB stack. And once again, as you can see, the footprint is quite low. And finally, GUIX can be, well, it's both a set of GUI widgets written in C, and it does clipping, drawing, event handling, those kind of things. And it will support graphics acceleration if your SoC provides it. And then essentially, you also have the ability to use GUIX Studio, which is a Windows application that will generate the C code to implement the user interface in your application. So this looks like this. So you see a screenshot of GUIX Studio there, and the kind of user interfaces you can build with it. On the right of my slide with this animated GIF. So in this case, I'm not showing GUIX Studio today. And to be honest with you, we are looking at options to replace the current tool with something which would be more cross-platform. But for the time being, this is Windows only. Although I heard about people running this in Wine on a Linux environment. Anyway, so if you're interested in the relative performance, and there's a typo on the slide. So this is the 2024 RTOS performance report, not the 2025. But in any case, that particular report compares Zephyr, FreeRTOS, and ThreadX from a performance standpoint. And so the benchmark suite used in the report is also open source and available, so you can do your own comparisons. But essentially, ThreadX is the fastest open source RTOS in the market as well. Now, what I will show today is leveraging a sample that we built, which is available on GitHub. And so that sample relies on a very specific board that we inherited from Microsoft. We don't see it on camera, my cable is too short. But anyway, you have a photograph of the board I'm using on my slide. Essentially, it's a nice little experimentation board with sensors built in, an OLED screen, buttons, and things like that. So really a nice kit. And essentially, from a developer tools perspective, really, you can get started with ThreadX using that particular board, or many of the boards we support, just using 4 specific ingredients. You need an appropriate C compiler for the target, and typically the GNU ARM embedded toolchain works perfectly fine. Of course, if you target RISC-V, then the GNU RISC-V embedded toolchain is perfectly fine as well. You need CMake, Ninja, and that's it. Of course, you need some kind of editor or developer tool, which is the 4th ingredient. But really, from an SDK perspective, ThreadX is very, very simple. And ThreadX has the particularity that it has no third-party dependencies. So in terms of the software bill of materials, it's ThreadX. That's all. And everything, including the cryptography stack, has been developed in-house, so to speak. So from that perspective, it's quite simple to manage. Now, if you need an IDE, and I would recommend that you have a look at TI IDE or its embedded variant in CDT Cloud Blueprint. And you will see me use this morning really the goal there is, if you like VS Code, and many of you, I suppose, watching do, but you don't like Microsoft's direction in terms of cramming Copilot everywhere, and of course monitoring everything that you do on the VS Code extension store and those kind of things, then TEA IDE and specifically CDT Cloud Blueprint are certainly options that you should have a look at. And the reason is simple. They use the same core components, but essentially TEA IDE and CDT Cloud Blueprint leave you the choice of whatever AI you want. So if you want to use Claude, if you want to use ChatGPT or some other conversational agent in there, you can do so. If you want to use Copilot, of course, this is fine as well. But really, in my case, I don't have agents configured in my IDE, and I can do this with TEA IDE and CDT Cloud Blueprint. So the difference between the two: TEA IDE is a supported product. You can see it as the successor of Eclipse IDE, built on the same core components as Visual Studio Code and using the same extensions, but connected with the VSX, OpenVSX extension store instead. And OpenVSX is managed by the Eclipse Foundation, so it's vendor neutral, and we don't put AI observing you all the time to sell you something. Okay, so this is vendor neutral and community driven. In the case of CDT Cloud Blueprint, this is TEA IDE. It's not as fully supported in the sense it's not a shipping product like TEA IDE is, but it comes pre-configured with everything I need as an embedded C developer. And this is why typically that's the version I'm using. But really, although they say on the CDT Cloud Blueprint it's not a shipping product, it works well enough, at least in my case. So the starter application that I will be using is on GitHub. So if you go to the Eclipse-ThreadX organization and look at the IoT Dev Kit repository, then you will find exactly the code that I will be using. And so if we look at the folders in that particular starter application, and by the way, you can scan the QR code on the slide, and it will bring you to the repository as well. There's a place which is our main source. Then, of course, there are bundled third-party libraries and app-specific files that are found in there that are pre-configured for the board that I'm using. Since it's using an ST microcontroller, then you've got, for example, all the HALs and abstraction layers and board support packages provided by ST Micro, which are part of the repo. And then, of course, we've got ThreadX and Nintex Duo as Git submodules, which means if you're cloning this, that's perfectly fine. Please do so. But don't forget to use the recurse submodule option to ensure that those particular submodules will be cloned in the appropriate way. Okay? And so that's the high-level overview. By the way, if you are specifically interested in ST micro boards, maybe you have a Nucleo lying around and you want to try out ThreadX, then this particular book would be of interest to you. I think I have a reference to it at the end of my slides, but anyway, please have a look at this book. It's full of good examples on how to work with ThreadX in ST micro environments. So we've got a bunch of files in there where essentially if you play with this application, by default, the main branch is empty, so to speak, in the sense it will just connect to Wi-Fi and that's it. So you put the Wi-Fi credentials in cloudconfig.h and start adding your code in the main file. But in any case, you will see that there are other branches, one called telemetry and another one called MQTT. And those branches contain additional code that help you discover ThreadX. So ThreadX is a young project. So of course, please have a look at the code, please have a look at the docs, and stay informed by joining the mailing list. And now it is the time, This is, the reference to the particular book. It's been published, once again, not in 2025. I did a global search and replace at some point on that deck, and it replaced 24 with 25, everything, everywhere. So published in August 2024, but still highly relevant. And this is a high quality book in terms of the samples that are contained therein. So my own sample for today's demo is quite a bit simpler, as you will see. So this is Eclipse CDD Cloud blueprint in action. And right now, you will see MX chip, AZ something something app. And so I'm looking at the cloud config file where I'm supposed to put my Wi-Fi credentials. So I created a one-off network for this purpose here. So don't try to hack me. Okay, this will not work. And I'm not telling you which game to play there, but you should have a look at this particular game if you are interested. Okay, and so there, if I go in the scripts subfolder inside the application, so you see I cloned this to C demo, so IoT dev kit, MX chip, AZ something, and in scripts, if we look at there's a build script for Windows, one for Linux, and the same deploy.bat for Windows and Linux. And when I say Linux, macOS is also supported. By the way, this is the repository, and you have extensive getting started application on how to start playing with that particular version of the application. And we tested this on Linux, Windows, and macOS, so it should work for you, hopefully. Anyway, so getting back to CDT Cloud Blueprint, what I will do now is just, as you will see, I am currently on the main branch, and we've got MQTT and telemetry branches that gradually implement some telemetry code to read the sensors on the board, and then MQTT, which exercises the NetX Duo in the NetX Duo and MQTT client inside to do cool stuff. So right now, what I will do is just build my code using the Windows version of the ARM GCC toolchain. And well, it's quite fast since in this case, of course, I tested a few times. The initial build should be a minute or two on your own machine if you're trying this, okay? And we see that the board has 120 kilobytes, and right now we use 57% of that, so roughly a little over 64K, since the application, of course, is configured to use both ThreadX and NetX Duo. So when I was telling you ThreadX is a few kilobytes itself, and then the network stack is roughly 50 kilobytes, as you see. This roughly matches my claims, and the reason why it's a bit higher is, of course, we have a number of dependencies in that particular test application that I'm not necessarily showing, but anyway. So all of this to say, it's fairly thin in terms of resource usage. And if I deploy this to my board, now I have a serial terminal watching the output on my little board, and you will see that once the flash is over, I will get Windows Explorer to pop up. So let's make this, and you see the application is trying to connect to my local network. And once this is done, you have information about DHCP, so the DNS client and the SMTP client all connected. So we are good to go. So this main branch, all it does is that. So if you want a starting point to just get started, then it's perfect. And if we look at the code, it's really, really straightforward. So we see here, we've got something mandated by ThreadX, which is called TX application define, okay? And in there, we establish our system tick, and then we define the thread, which is the Eclipse ThreadX thread. That's a lot of ThreadXs and threads. And so what it does is it's using a specific function, which is above in my code. And then it instantiates the default properties for the thread and get it started. And the main just called board init, and then called ThreadX kernel enter. And ThreadX kernel enter will call this TX application define thing, since it's the way it operates. So apart from that, there isn't much there. So we've got some defines with the default value for the stack and the thread priority and things that are configuring the thread there. And we've got the ThreadX entry, which is the entry point for the ThreadX thread. And all it does is, printing some information there, and call the network initiation feature pre-configured in this starter application. And that's about it. And as you can see, all of the rest happened magically. So now I'm connected to my Wi-Fi, but that's all the application does. So to keep things short, I will switch to the MQTT branch and show you how we implement code to read the sensors and how we send MQTT messages to report about the telemetry that the board is finding. So in order to do that, first, I will reset my GitHub repository to ensure that we have a clean environment. No, that's hard and not force. All right. And then I switch to the MQTT branch. So git checkout MQTT. All right. And you see now there's much more code in there. So we'll review this. And of course, I need to put back some information there. And in particular, username and password for my Wi-Fi, and maybe a different host name for this. But you can see that we've got other properties now. So there's an MQTT client name defined. And we have a local broker IP. In this case, I'm using testmosquito.org. So that's the current IP address for this. Hopefully, it will still work. And then I've got publish and subscribe for my MQTT. So I will be publishing on a topic called incoming. And no, I will receive messages on a topic called incoming. And I will publish on a topic called telemetry. And then there are other values that are defined for my MQTT client in there. Okay, so going back at my main, there are, as you can see, many new things in there. So we see this concept of TXQ called MQTT-Q. And essentially, this is the way that processors in ThreadX can communicate with each other. You have this concept of events, and you have this concept of queues, and you can send messages from one thread to another in order for them to communicate with each other. So essentially now I have a telemetry thread that reads the sensors and publishes information. And then I have an MQTT thread that deals with the MQTT communication, okay? And this, of course, requires some shared byte pool. And of course, we see here two distinct threads. So one is my telemetry thread and one is my MQTT thread. Okay, so when I look at my application define, then of course it's doing much more. So here we allocate the message queue. Okay, TX byte allocate, yada, yada, yada. Here we establish our message queue from there. So we allocate some memory for it, and then we create the message queue itself. And then we create our telemetry thread. And then we create our MQTT thread. Okay, so we have two distinct threads running. One is about the sensors, one is about the MQTT. So the telemetry thread is in there. Okay, and you see that, well, I've got a utility to compare float arrays because I got fancy, and essentially it will just send messages about telemetry if the telemetry changed. And since we are watching several sensors on this little board, they change all the time. So, it nearly never happens that a message is not sent, but this could be changed with a different sampling rate or a different tolerance for the sense or something like that. Anyway, so we see here this comparison, whether, the old data change versus the new data. So I'm comparing sensor readings. And here, this get sensor data buffer is really a way to do a nice print out of the sensor information that we are getting. That's another utility function. So in this particular case, we have an ifdef here that will log more detailed information to the serial port. Okay, in this case, it's disabled because we'll do this through MQTT. And so the entry point for the telemetry thread is there. And here, essentially, in an infinite loop, we read specific sensor data in that particular block of code. Okay, and those functions are defined elsewhere in the application. Of course, they are defined by some of the codes that we implemented, in other sections that I'm not showing. But essentially, this is using the hardware abstraction layer behind the scenes in order to get temperature data, pressure data, humidity data, and that kind of stuff. Okay. And then if that data changed, then you see here we set a flag. We set a flag from this thread to the other thread to tell the MQTT thread, hey, you have to send a message because our telemetry changed. And then essentially the thread sleeps at the end. So, so that we don't constantly read the sensors and constantly send messages. So we sleep for an interval to ensure that we keep things under control. Okay. So if I look now at my MQTT client, and I will start at the bottom there. Okay, so the entry point for this thread is very simple. Okay. Essentially, we say that we start the thread, we initialize the network, and then we have a function that does the actual work, which is called. Okay, so if I get to that function, it's a bit longer, but essentially, the MQTT thread work function will create an instance of the NetX Duo MQTT client. So a client name, etc., etc. So there are several properties in there. And then it registers a function to call in case of disconnection. And after that, of course, we need to create on this side the event flag as well. And in this particular case, I configure NetX Duo to really use MQTT, not MQTT, but TCP/IP version 4. So I set specific properties that I need, and I connect to the MQTT broker here. And then to keep things interesting, we do two things. So here, okay, we subscribe to an MQTT topic on this particular line. And here we register a specific function to call when we receive a message. And then once we've done all of that, we are ready to listen, okay, to subscribe to our flag. So essentially, we check if a flag has been set up by the other thread. And in this particular case, we receive a message. And otherwise, if we have a different flag, which is about the fact that we are ready to send a message because the telemetry changed, then we call send message. Okay, and those things are above in the file. So you see the notification function there. You see the receive message there. So all we need to do is to get the message from the MQTT client. And in this case, we just print whatever has been received. And the send message, as you can see, is simple as well. So we just publish on the MQTT client. So you see, ThreadX and NetX Duo do most of the work for you from that perspective. So it's a very productive way to work with TCP/IP and MQTT in an embedded environment. My code is fairly simple and straightforward. And of course, all I'm showing, you can go in the repository on GitHub and look in detail at what I showed, even if you cannot run it because you don't have the same board as me. So just switch to the MQTT branch, and then you have the exact code that I ran you through this morning. Okay, so now let's try to make this work. Hopefully the IP address didn't change on our broker. We'll see. So first I need, of course, to rebuild my application because the code changed a bit. And you see that I'm now using a bit more memory because now there's the MQTT client incorporated and all of that. But it's still, we still have some headroom. We are not using 70% of our memory. So that's not too bad, given everything this application does. And of course, now that I deploy, so we will see that I will get new output on my serial port for the board once it's finished flashing. And so, of course, it needs to connect to our Wi-Fi network. so we'll get the same output. And after that, it needs to try to connect to the MQTT broker. And now it's failing. Typically, when it does that, it's maybe because the IP address for the broker changed. So what I will do is do a quick lookup for this. And yes, indeed, it seems that we've got a different address. So 5436. 5436, 178, and 49. So this shows you that I'm not faking this demo, since things are not going as expected. So let me redeploy. And now it should be able to connect to our MQTT broker once the application restarts and reconnect to the Wi-Fi. So please wait a few seconds. All right, so we've got this. So trying to connect to the Wi-Fi, this typically works. And then it will connect to the MQTT broker and start publishing MQTT messages that provide the telemetry. So we see published message. Okay, excellent. So now one way to check this is, of course, to subscribe ourselves to the MQTT broker. So I'm using here Linux inside the Windows Linux, the Windows subsystem for Linux, and I'm using the Mosquito Pub and Mosquito Sub utilities. So in this case, I'm subscribing to my topic that the microcontroller is publishing to, and we see a neatly formatted text with the sensor readings. So right now it's 25 degrees here with 41 of humidity. It's a bit high. It's not an especially precise sensor, I should say. Let me check. No, it's it's really not a very precise value. But anyway, that's the readings from my sensors. Okay, and of course, in this case, I made it text so that it's easy for you to parse it and read, but it could have been JSON, could have been anything, right? MQTT is easy in that way. And now let's try something else. Let me bring my serial output on the screen. And what I will do is essentially, I will publish a message and it should be received by the microcontroller. So once again, I'm using Mosquito Pub here. And we say, hello again, ThreadX. And we see that the message has been published on ThreadX AZ something incoming. And the message is, hello again, ThreadX. And all the while, the microcontroller was continuing to publish information on my topic, which means if I subscribe again using Mosquito Sub to the topic, yes, you can see that it's still working behind the scenes. So this is a worldwide tour of a very simple ThreadX MQTT application. But as you can see, the code in itself that I had to write is not that huge. Most of the board stuff, the BSP, the HALs, and all of that, typically when you work with ThreadX are supplied by your particular board vendor or your particular SoC vendor. And at the same time, really, I hope that I gave you the idea to try TIA IDE or CDT Cloud Blueprint, because if you love VS Code, this is literally VS Code, but without the bad telemetry, without the bad part, under vendor-neutral governance at the Eclipse Foundation. And if you want AI, you can get it. And if you don't want it, then you keep it away. And it's really a tool that you own as the developer and which is not owned by any private organization. All right, so enough. That's it for this particular demo. Thank you so much for listening to me. And now, if you have specific questions, happy to answer them. And by the way, this is the little board that I was using. Just disconnected it now so that you can see it. All right, so thank you very much.
Thank you so much, Frédéric, and to Sebastian as well for your wonderful presentations. So just a reminder to everyone, if you have any questions, please feel free to copy-paste them or add them into our chat or ask a question tab. I don't see any questions at the moment, but I think we can give a couple of minutes to everyone to think a little bit. And meanwhile, we will do the raffle. So I will just share the screen in a second. There you go. Yes, I think you should be able to see it. So we will have 3 winners. The first winner will get a free OCX 2026 ticket. Second and third winners will get a €50 off OCX swag shop. So I already added all the attendees. So let's start the raffle. There will be a short countdown. Just a few seconds left. And we can see our winners. So Henrik Gomez, you won a free OCX 2026 ticket. Congratulations. And Digitally
Nice.
Squared, unfortunately, I don't have your exact name. And Harold Macamal, you won a €50 voucher for our swag shop. So we will contact you separately about that. And now I will just stop sharing the screen for now. Let's double check if we have any questions. We only have some nice comments with thank yous, but I don't see any more questions. And with that, thank you so much once again, Frédéric and Sebastian. Really appreciate having you here and hope to see you at our future webinars. I see there are more and more nice comments coming in. And I wish everyone a great Friday and a great weekend ahead. Thank you.
Have a nice weekend. Thank you so much for hosting.
Thank you. Bye-bye, guys.